Hello. So in this video, we are going to continue our discussion on comparing the sizes of finite sets, infinite sets. Now, in answering questions about sizes of infinite sets, we have a theorem which is of great importance due to Cantor. So that is theorem 6, Cantor's theorem. Now, before that, you have some exercises, easy problems. So they are labeled as exercises to show that Q is countable. And then exercise 9 defines real numbers as algebraic and transcendental, right? So algebraic means that so over the rationals. So algebraic over the rationals. So if a real number exists algebraic over rational numbers, if that real number is the root of a polynomial equation with rational coefficients, right? Like this one. So this is a 8th degree polynomial, and it has rational coefficients. So if a real number is a root or a zero of such a polynomial equation, then it is called an algebraic number over the rationals. Now you have to observe that having here the coefficient of x to the n as 1 is not an issue, right? And then we call a real number x is transcendental if it is not algebraic, right? All right. Now you might think that the numbers that are transcendental, right, they had to be a few, but that is not true. In fact, algebraic numbers are countable and transcendental numbers are uncountable. So I'm going to leave these two exercises for you, right? And then we'll prove Cantor's theorem, right? So the Cantor's theorem says that it says that there is no surjective function from A onto the power set of A, right? Let me zoom this out. Right, perfect. So here A is an unempty set. So this theorem asserts that there is no onto function from A on the power set of A, right? Now, when you think of this theorem, it should occur you to that if A is a finite set, then the conclusion in this theorem is quite obvious, right? A is finite, right? So this is a non-empty set. So if A is finite, then A has n elements, right? Has n elements for some positive integer n, right? And then how many elements are in the power set of A? So you know that the power set of A has 2 to the n elements, right? So we denote it by this notation, right? Also, we use this notation. This has 2 to the n elements, right? And it is quite obvious that there can't be a surjective function or an onto function from a set with n elements to a set with 2 to the n elements, right? So when A is finite, the conclusion in this theorem is uh, obvious, right? But when A is infinite, then things are different. Because then we can say the power set of A has 2 to the infinite elements, right? We can say that, okay? So we have to come up with a different argument than here to conclude that there can be a surjective function from A onto the power set of A. Hope that this bird doesn't disturb you, right? So hopefully the bird will stop shouting. So we'll continue our discussion on this theorem, right? So in the case of A being infinite, so the proof of the theorem had to wait an ingenuity of a person like Cantor. So he came up with an ingenious idea to show that even when A is infinite, there is no onto function from A onto the power set of A, right? So we'll look at his idea while we write the proof of this theorem. So A is a non-empty set, right? And then we are going to prove this by prove by contradiction method. So suppose that there is a surjective function f, right? From A onto power set of A, right? So f from A onto the power set of A is surjective, right? Now we have to get a contradiction by assuming that that there is a surjective function from A on the power set of A. So then, by the proof by contradiction, we can say that well, there is no such function. Now, how do we get this contradiction? Now, for this, Cantor came up with this ingenious idea to look at the set. So he considered this set. Let B be the set of elements in A, right? Such that A does not belong to f of A, right? Now let's do some thinking here. Now, if there's a surjective function from A onto the power set of A, right? So so we are going to depict A by this long oval-shaped figure and the power set of A. So maybe a bigger one, right? So for each element in A, if assigns a subset of A, right? Because the elements of the power set of A are subsets of A, right? So if you take an element A, then the function f assigns, of course, we label it as f of A, but f of A is a subset of A, right? It is a subset of A, right? So then this makes sense that letting B be the set of elements in A such that I have done a mistake here. A doesn't belong to f of A, right? So f of A is a set, and we can consider this set, which is a subset of A. It is a subset of A because so B is a subset of A, right? It is a subset of A because we say that A belongs to A, right? So therefore, B has to be subset of A, right? Now, for every element in A, this set B exists, right? It could be empty, right? It could be empty. And A, for a given element in A, this simple A may or may not be in f of A, right? So if for every element in A belongs to f of A, then this is empty, B is empty, right? And if for every A in A, right, if A belongs to f of A, then of course, A doesn't belong to f of A, then of course B is equal to A, right? So B could be any subset of A, right? Okay, now let's see what Cantor does next, right? Right. Then he asks this important question. I got to remember that Cantor wrote his PhD dissertation. It was named as something like asking questions is more important than finding answers, something like that. So you can find out the title of his PhD dissertation or PhD thesis. So here he asked a very important question. The question is, does A belongs to B? Wait a minute. Now, before that, we need to look at this B. So B is a subset of A, right? So it is an element here, right? So I'm going to put a dot here, right? So this is B, right? Since B is a subset of A, B is an element of the power set of A. So by a dot, I denote an element of a power set of A, but it is a subset of A, right? Now there is some element here, A node, right? Which this F assigns to this, right? In other words, F of A node is equal to B, right? Because F is onto. Then Cantor asks this question: does A naught belongs to B? Right? So that's the important question Cantor asked. And because he asked an important question, he was able to answer this question whether there is a surjective function from A onto the power set of A. Right. So now we have to say that now since F is onto there is A naught belongs to B belongs to A, right? Let's erase it. Such that F of A naught is equal to B. Okay, right. Now the Cantor's great question, right? It's a great theorem because he asked a great question, right? Does A naught belongs to B, right? And let's see why this is a great question, right? So if A naught belongs to B, right? If, right? So that means that A naught belongs to F of A naught, right? Now, how did we define B? We define B to be all the elements in A such that A doesn't belong to F of A, right? Here we have this A naught, which belongs to F of A naught. So that means A naught does not belong to B, right? Because B contains all the elements in A for which that element is not in F of that element. So here we have A naught which belongs to F of A naught. So therefore A cannot be in B, right? So we have a contradiction, right? A naught belongs to B implies A naught doesn't belong to B, right? Then by the excluded middle, sorry, excluded middle, right? There's only one other option, that is that A naught doesn't belong to B, right? A naught doesn't belong to B. So if that is the case, then A naught does not belong to F of A naught. So it means that A naught belongs to B, right? Because A naught doesn't belong to B means that this is true, right? This part is true. So that means A naught doesn't belong to F of A naught, but F of A naught is B. It is B, right? Because that is the set to which A naught is assigned. So then we have A naught doesn't belong, A naught belongs to B. So A naught doesn't belong to B implies that A naught belongs to B. So we have a contradiction. That means our initial assumption is not true. That means there is no surjective function from A onto the power set of A. Okay, if A naught belongs to B, right, then A naught does not belong to f of a naught, right? So a naught does not belong to B, since f of a naught is B, right? So therefore, a naught belongs to B implies a naught doesn't belong to B. This is a contradiction. Therefore, a naught has to be not in B. That is, a naught does not belong to B, right? So, but a naught does not belong to B, right, implies, right, a naught does not belong to f of a naught, since B and f of a naught are the same, right? So, a naught wait a minute, now a naught doesn't belong to B. Yeah, that is true. A naught does not belong to f of a naught. So that means a naught belongs to B because as the way we define B, right? It consists of all the elements, right, in A such that A doesn't belong to f of A, right? So A here, A naught doesn't belong to f of A naught. So therefore, A naught belongs to B. So therefore, a naught doesn't belong to B implies a naught belongs to B. Again, a contradiction. So therefore, see the both cases, right? Consider the two cases, right? A naught belongs to B. A naught doesn't belong to B. So that those are two cases, right? And both cases lead to contradictions, right? So therefore, our initial assumption that there is a surjective function from A onto the power set of A is not correct. So therefore, there is no surjective function from A onto the power set of A, right? So here we finish the proof. We draw the Helmholtz's tombstone. Now let's go over the proof again, the writing. We have to make sure that there are no typos, no mathematical typos, right? So let's see. So I'm going to read this. Let A be an analytic set. Suppose that there is a surjective function f from A onto power set of A. So f, right, is from A to power set of A onto, and then we consider this set B. Now since f is onto this a naught in A such that, fine, and that with question. So if A naught belongs to B, then A naught doesn't belong to f of A naught, because that's the way we defined B. So this is, by the definition of by the definition of B. So you can add it here if you want. By the definition of B, right? So A naught doesn't belong to B because A naught is equal to B. Since f of A naught is equal to B, right? So therefore, A naught belongs to B implies A naught doesn't belong to B. And then yes, it is a contradiction. And then A naught, the other case, A naught doesn't belong to B. So that implies that A doesn't belong to f of A naught. So here, by the definition of B, right? So A naught belongs to yeah. So this this is not because of that. So this should be here, right? But here it should be so A naught doesn't belong to B implies A naught doesn't belong to f of A naught since A naught is equal to f of since B is equal to f of A naught, right? That's why we say here that A naught doesn't belong to B implies A naught doesn't belong to f of A naught, right? And then this conclusion by the definition of B. So there's fine, again a contradiction, right? All right. So we have done the proof. Now the Schröder-Bernstein theorem, proof of the Schröder-Bernstein theorem, right? So before I start this proof, I want you to think about the theorem, right? So it says that that if you have two, so A and B are non-empty sets, right? And we have two injective functions from A into B and B into A, right? So then there has to be a bijection between the two sets. That means A and B are numerically equivalent, right? Now, if A and B are finite sets, right? If A and B are finite, right? Then the fact that there's an injective function from A into B, we can say that so if A and B are finite, then from the fact that we have an injective function from A into B, we can say that the number of elements in A has to be less than or equal to B, right? And from this, we can say that number of elements in B has to be less than or equal to the number of elements in A, right? So if we have these two inequalities, we can say that the number of elements in A is equal to the number of elements in B, right? I need to come up with a appropriate argument using the theorems we did earlier, right? So all this have to be concluded in terms of injective functions, surjective functions, right? But it can be done. So when A and B are finite, Schröder-Bernstein theorem is not a great conclusion, right? Like in the Cantor's theorem, right? But what happens when A and B are infinite? Then we cannot give this argument, right? We cannot give this argument, so we have come up with a different argument, right? So I want you to pause and think, right? And then I will discuss the proof of this, right? So pause and think, okay? Right. Okay, so let's continue with the proof of Schröder-Bernstein theorem. Now, for this theorem, to prove this, they came up with a great idea. They came up with the very same idea because what happens is that often a mathematician finds a proof of a theorem, right? But then lots of other mathematicians come up with different proofs, right? So it could be the case here, right? That the idea of ancestors that I'm going to use to prove this theorem here may not be the idea of the Schröder and Bernstein, right? But since they came up with the original proof, we call this theorem the Schröder-Bernstein theorem. But now I'm going to use the concept of ancestors, right, of elements in A and B, right? I think this is due to maybe Burkhoff. So you need to find out who came up with this idea, right? Okay, now his idea. So let's say that I'm going to depict the set A this way, right? And then long, oval-shaped, but it doesn't look like an oval shape. B, right? Let me change the letters. Anyway, it doesn't matter, right? Okay, so we start with an element in A. So this dot denote the element, right? And we call that element its zeroth ancestor. It makes sense, right? So I'm my zeroth ancestor, right? Now, who is my first ancestor, right? So then I don't, so in my case, it would be my parents. I had two of them, right? Mother and father. But in this context, only one ancestor. So you have to go back, right? In my case, my mother and father. Here we go back, right? Via, right, the function g, right? So from A to B, right, we have so we can use f and g. So we have to go back using f inverse to g inverse, right? So if g inverse of A exists, right? So G is from B to A, right? And then you know that G inverse, right, exists, right, from G of B to B, right? So G of B is a subset of A, right? It is a subset of A. So if A belongs to G of B, then of course the G inverse of A exists, right? So we go via G inverse, right? And then this element G inverse of A, right? So undo G inverse of A, right? It is called the first ancestor of A, right? Right. So this is the zeroth ancestor, and this is the first ancestor, right? And it could be that we can go back, right, using F inverse, right? If F inverse of G inverse of A exists, right? So F inverse, right, it actually is a function, right? F inverse. So F is a function from A to B. So F inverse, right, is a function from F of A, which is a subset of B, right, to A, right? So if G inverse of A belongs to F of A, then F inverse of G inverse of A exists, and we call this the second ancestor of A, right? Now again, you need to pause and think, right, of this concept of ancestors, right? So I said ancestors of elements in A. So this is we are talking about the ancestors of the elements of this element A in A, right? So we can do the same discussion of an element B in B, right? So I want you to pause and think, right, of this idea of uh, ancestors, right, of elements in A and B. You need to play around with this, play with this concept, right, before we proceed to the proof of the theorem, right? So you should be able to see that there are three kinds of elements in A according to the number of ancestors it has, right? So this element in A, right, it may have, right, right, an odd number of ancestors, right? So A has an odd number of ancestors, right? So we denote this by O, right? A has an odd number of ancestors. That means that for such elements, G inverse of that element exists because it has to go at least once, right? At least it has a first ancestor, right? But it could be that it has a third, it has three ancestors, right? First, second, third, right? So in that case, it comes back, right? Via G inverse. So this one exists, three ancestors, right? So 1, 2, 3, right? Or you could have 5 ancestors. Go back to A and come back, right? So 5 ancestors, right? Here 1, 2, 3, 4, 5, right? Or we could have an element in A, right? It has an even number of ancestors, right? Even number of ancestors. So this we denote by AE, right? So it could be that it has only itself as the ancestors, right? It means that G inverse of A does not exist, right? So it doesn't go back, right? It doesn't go back, right? So it has 0 ancestors. So that is 0 is an even number, right? Or it has 2 ancestors, right? So it stops here, 2 ancestors, or stops here, 4 ancestors, right? And then, of course, we could have elements in A, right? This, right, ancestors, it could have infinitely many ancestors, right? A has an infinitely many ancestors, right? Right? And this we denote by AI, right? This goes without an end, right? Continues forever, right? Continues forever, right? Until the end of time, right? All right. Now it can be easily seen that these sets form a partition of A, right? They form a partition of A. So if this is set A, so we have a partition, right? Partition, right? A naught, sorry, AO, AE, AI, right? It could be that some set is empty. In that case, we don't have a partition of 3 sets, right? Maybe we have a partition of 2. Maybe so for some functions, A naught, AE are both empty. So it is simply the whole set, right? And we can similarly define BO, BE, and BI, right? Again, they form a partition of B, right? So exhaustive and exclusive, all right? So I want you to pause and think, right? This concept of ancestors and play with this concept, right? And then we'll do the proof, okay? Okay, let's continue a proof of the Schröder-Bernstein theorem. Um, so, proof. So let A be non-empty sets and F from A into B and G from B into A be injective functions, right? And then we are going to define ancestors. Let A belong to B. So A is called this zeroth ancestor of A. Sorry, simply, if G inverse of A exists, then G inverse of A is called the first ancestor of A, right? If F inverse of G inverse of A exists, then it is called the second ancestor of A, right? Similarly, nth ancestor of A defined, okay, for n belonging to Z plus, for n a positive integer, right? Now define A O. A belongs to A and A has an odd number of ancestors and AE, A belongs to A, A has an even number of ancestors and AI, A belongs to A has, okay, A has an infinite number of ancestors, right? Right. Similarly, define A, sorry, AO, BO, BE, and BI, right? Now define um, f from A into B by um, f of A is equal to uh, f of simple f of A if A belongs to AI union AE, right? And um, genus of A if A belongs to AO, right? Now this is our function f, uh, which is a bijection, right? So show that capital F is a bijection, right? So you have to show that capital F is well defined, it is one-to-one and onto, and then we are done, right? Once again, pause and okay, and think, right? Okay, let's say pause, think, and work out, right? Okay, so we'll continue the proof, but before that, I want you to pause, think, and work it out. All right. Okay, let's continue our proof. So we're going to show that this F is a bijection, right? So uh, first we'll show that F is well defined, right? So why is F well defined? Right? Uh, Now, um, so we have actually two cases. One is that when A belongs to AI union AE, right? So case one, uh, A belongs to AI union AE, right? So in this case, uh, f of so capital F of A is well defined, right? Since um, simple F of A is well defined, right? And case two, uh, A belongs to AO. So in this case, F of A is well defined, since genus of A is well defined, for any A in AO, right? Because it means that it has at least one ancestor, right? Because it has an odd number of ancestors. So therefore, genus of A exists, right? So that means genus of A is well defined. So F of A is well defined, right? So F is well defined, right? Now F is one-to-one, right? So how do we show this? Okay. Once again, you can pause, think, and work it out. All right. So I'm going to give you time. Okay, let's continue. So we take two elements, let A prime belong to A, right? So then we're going to consider three cases. Case one, so A and A prime both belong to AI union AE, right? Right. So now, if f of A is equal to f of A prime, right? This means that, like in this case, capital F of A is equal to simple f of A, and capital f of A prime is equal to simple f of A prime. So this means that A is equal to A prime, since simple f is one-to-one, right? All right, so in that case, we show that f of A is equal to f of A prime implies A is equal to A prime. Now, how many more cases do we have? So, by looking at the case one, case two has to be both A and A prime are in AO, right? Right. So in this case, so f of A is equal to f of A prime implies that if then capital AO, then of course f of capital F of A is G inverse of A, right? And capital F of A prime is G inverse of A prime, right? So this implies that A is equal to A prime, since genus from, now G is from B to A, right? And G inverse is from G of B to B, is one-to-one, right? Right. So in case two also we showed that this implication is true, right? And then we have at least one more case, depending on how you write it, right? Now, we consider two elements, right? And then one case is both are in AI union AE, and the other one is both are in AO, right? Then you can say A is in AI union AE and A prime is in AO. That is case 3. And case 4 is A is in AO and A prime is in AI union AE. But we can say without loss of generality, right? So case 3, without loss of generality, let A belongs to AI union AE and A prime belongs to AO, right? So then we have reduced one case, right? So what happens here when we have f of A is equal to f of A prime, right? Right. So this means that, let's see. So since A belongs to AI union AE, we have that capital F of A is equal to F of A, and then capital F of A prime is G inverse of A prime, since A prime is in AO, right? So now what can we conclude here? Okay, let's do some thinking here. So now if A belongs to AI, right, then we can say that f of A, right, is an element in B, right? So um, so f of A goes forward, right? So it's like this, right? We have this A and B. So A is an element in AI, right? And then since it is in AI, so this goes forever, right? And then here we go forward to f of A, right? And this is in B, right? But for this element, this also goes forever. So that means f of A belongs to BI, right? It belongs to BI, right? So if A belongs to AO, no, AE, right? Then this stops, right? Starting from A, goes like that. It stops in A, right? It stops in A. So it has to come back and stops because it has an even number of ancestors, right? It stops here, right? And then when you take f of that element, right? So this is going back, right? Going back. So this is going forward, and this goes forward, right? So this element, sorry, now this comes back from B, it comes back through F inverse, right? So when you take off F inverse of this element, it goes back. And this element, which is F inverse of A, right? Is it, no, actually, we take F of this element, right? F of this element, right? So that means we go back to B, right? Sorry. Okay, let's do it again, right? Let's do it again, right? So here, I think this is clear, right? Maybe I got you confused here, right? So if A belongs to AE, that means you have this element in A, and this goes like this and stops here, right? So this is, so that stops it because it has an even number of ancestors, right? But if you take f of A, right, then it goes forward, or in a way, so this element, right, so it has an odd number of ancestors. It's an element in B, and it stops in A, right? So one more ancestor is added. So here you have even number of ancestors, and then with this guy, right, uh, it has an odd number of ancestors, right? So A belongs to E implies that f of A belongs to B, E, right? Now, what about, so now here, A prime, right? It belongs to AO, right? So here, A prime, so it belongs to AO means that it has an odd number of ancestors, right? So it ends up here, right? And then when you take G inverse of A prime, right? Um, it is this element, right? Okay. And then A prime has an odd number of ancestors, right? And G inverse of A prime has even number of ancestors, right? So we can say that G inverse of A prime belongs to B, E, right? Um, sorry, now this has to be, right? A belongs to f of A, and f of, sorry, A belongs to A implies that f of A belongs to BO, right? And here, genus of A prime belongs to BE. I found that mistake because what happens here is that uh, this one, f of A belongs to BI union BO, right? And this guy belongs to BE, but BI union BO, these two sets are disjoint, right? Disjoint. So we have a contradiction, right? So before I write this, I want you to pause and think, okay? Okay, so let's write this down. Okay, now f of A belongs to AI if sorry, BI if A belongs to AI, and f of A belongs to BO if A belongs to AE, right? Okay, let's get more space here. Therefore, f of A belongs to BI union BO, right? And G inverse of A prime belongs to BE, but BI union BO intersection BE is empty. So therefore, this is a contradiction. What is the contradiction? The contradiction is that having f facial f of A prime in this case, right? So therefore, we can conclude that so therefore A and A prime. So therefore, we can say that sorry about that. So we have shown that sorry, that so therefore f is 1 to 1, right? Okay, how do we show that f is 1 to 1? Sorry, f is 1 to. Okay, we start by taking an element. Let B belongs to B, right? And we'll show that there's an element in A such that capital F of A is equal to B, right? Now, to find this element, and using the definition of capital F and some thinking, we have two cases to consider, right? So this doesn't come out of the blue, right? These two cases, it comes from thinking about what to do and what this function capital F is, right? So case one is that B belongs to BI union BO, right? So in this case, right, B has at least one ancestor. So B has at least one ancestor, right? So that means affinities of B exists, right? So therefore, affinities of B exists, right? Because from the element B in B, we can go back via F, right? So affinities of B exists, right? You can see that affinities of B, right, is in affinities of B is in AI if B is in BI, right? Because this going back infinite time doesn't change, right? And then affinities of B is in AE if B is in BO, right? So BO means that it has an odd number of ancestors, right? And then you go back once, right, via F inverse, right, like this. So here A, here B, right, and this is this B, right, and you go back via F inverse. So this is F inverse of B. So if B has an odd number of ancestors, then F inverse of B, sorry, this has to be simple B, right? So let's use some other color here, yellow. So F inverse of B, right? So this one has one less. So then it has to be in AE, right? So exist and F inverse of B belongs to AI union AE, right? So therefore, capital F of F inverse of B, it is equal to, by the definition of capital F, right? It is equal to F of F inverse of B, right? And this is B, right? So therefore, we found an element in A, right, such that it is this element. F of that, capital F of that element is B, right? So in this case, we have shown that this capital F function is onto, right? So case 2, B belongs to BE, right? B belongs to BE. So we could have 0 ancestors or a positive even number of ancestors, right? So B is in BE. Yeah. So let's draw. Yeah. So this okay, B, A, right, right, right. So we can go forward via G, right, and we get G of B, right. Now here, since B has an even number of ancestors, right, this, right, ends in B, right. Now this element is in A, G of B, and it has an odd number of ancestors, right? So therefore, G of B belongs to AO, right? Therefore, F of G of B is equal to G inverse of G of B, and this is equal to B. So we have found an element G of B in A such that capital F of this element is B, right? So we have shown that capital F is onto, right? So we have shown that capital F is well defined, one and onto. Therefore, capital F is a bijection, right? So therefore, A is numerically equivalent to B, right? So that's the end of the Schröder-Bernstein theorem. Now, again, you have to go through the proof and see that there are no typos, mathematical typos, right? And then you have some nice problems here, not exercises. So that means a little bit difficult than exercises, right? And you should try them, okay? Where are these exercise problems? The problems here, see? Let's take it here. Right. So there are three nice problems, right? So first problem is that you need to show that the power set of the set of positive integers is equal to R, right? And then you can deduce that R is uncountable because it's very easy to see that that this is uncountable, right? Uncountable, right? Right, because there is no surjective function from Z plus into P of Z plus by the Cantor's theorem, right? So then we have theorem, another theorem that we did earlier, right? So so there is no surjective function from Z plus onto this one, right? So if if the partial Z plus is countable, then there is, right? And since there is no such surjective function, it follows that the partial Z plus is not countable. It is uncountable, right? And then here very nice problems, right? So try them, right? And I will see you again in another video to continue our discussion on comparing the sizes of sets, both finite and infinite.